Hi folks, we're going to take a look at the solution to number 19 on page 158. Okay, so this is one of these problems where you have a vehicle that leaves a point. So in this case here, we've got a train leaving a station, travels north, and then you have another train that's moving towards that station, heading due west, and they want to determine at what time the trains are closest together. Okay, so we've seen this type of problem before, so let's start by getting a good diagram in. Okay, so if we say this point represents the station, so we have one vehicle that's traveling north. Okay, so let's use this arrow to represent the distance it's traveled in some amount of time. And then you have another train that's moving due west. Okay, so it's starting somewhere here, east of the station, and it's moving due west. Okay, and so that represents how far it's traveled in an unspecified amount of time. Okay, so we know that this train here is traveling at 100 kilometers an hour. So after t hours, it'd be traveling 100 t kilometers. Okay. Now this is where things get a little dicey, because this one's going to be traveling at 120 t kilometers after time t, since it's going 120 kilometers an hour. But what I'm trying to do is I'm trying to minimize this distance here between the two trains. Okay, so it looks like what I want to be working with is this right angle triangle here, so that I can use Pythagoras. But this is where we got to look at the times, is that this whole process initiates at 10 a.m. and we know that this train arrives at the station at 11 a.m. So that means this train in total will be traveling 1 hour. So that means that the distance from the starting point to the station, okay, will be 120 kilometers. So that means that we can represent this length here by 120 minus 120 t. And now what we have is we have a relationship between the distance that we're looking for and the two distances for which we have information. So this is now going to allow us to write an equation for that value that we're trying to optimize. Okay, now I'm going to write the unsquare rooted version here. So we'll say that d squared is equal to 100t squared, okay, plus this expression 120 minus 120t squared. Okay, and I'm going to choose to work with implicit differentiation. Okay, so the only other thing we need is we need our constraint on the variable here. So we know that we're only interested from 10 a.m. to 11 a.m. from when we start to when that second train arrives at the station. So I'm going to let t vary between 0 and 1, okay, where t represents time from 10 a.m. Okay, so instead of working with 10 and 11, I'm just going to work from 0 to 1, understanding that t represents the time from 10 a.m. Okay, so now we'll go ahead and do the calculus portion. So let's take the derivative here with respect to time. So I'm going to apply the chain rule there. So this becomes 2d d prime, okay, where this is derivative with respect to t. And here, instead of multiplying everything out, I'm just going to use a chain rule here. So this is like my u, so 2u, 2 times 100t times the derivative of 100t is just 100. Okay, and same thing here, 2 times 120 minus 120t to the exponent 1 times the derivative of this thing here, which is just negative 120. Okay, I can divide both sides by 2. Just get rid of those coefficients of 2, makes things a little easier. So here we have d prime is equal to, here I'll even just leave it as 100 squared t. This is going to be minus 120 squared, and then plus 120 squared t, all over whatever the distance value is. Okay, which I actually don't care about because I'm interested in when this derivative is equal to 0. So I'm only interested in the numerator. Okay, so here we've got, let's add these together. Okay, so let's get our calculator here. So we have 100 squared plus 120 squared. Okay. So that gives us, oh, sorry, I just realized I did multiplication. That seemed like way too big a number. So let's try that again. 100 squared plus 120 squared. That's why it's always good to question the answer you get from the calculator. Okay, that looks a little more reasonable. So we got 24400 times t equals, and I'll bring that to the other side. So 120 squared is 14,400. So t is equal to 14,400 divided by 24,400. Okay, and that's 0.59. Okay, so we have to determine whether this, this is indeed a minimum, or perhaps does the minimum occur at one of the two endpoints, since this is a closed interval. So we'll test d at 0. Okay, so if I stick t equals 0 here, so that portion's going to just disappear. That's going to disappear, so I'm going to end up with 120 squared, but I have to take the square root of that to find d. So square root of 120 squared is just 120. So I didn't even need to use my calculator there. Let's check d at 1. Well, d at 1, we notice this thing is going to be equal to 0, because you're going to have 120 minus 120. So here we're going to have the square root of 100 squared, which is just 100. Okay, we could have probably figured this out from my diagram also, but might as well use our function. So let's test d at 0.59 and see if it gives us something less than 100. Okay, so here I will get out my calculator. So we've got 100 times 0.59. Okay, I'll square that. Okay, plus 120 minus 120 times 0.59. Okay, and we'll square that. Okay, and then we have to take the square root of that because we want the actual distance. Okay, and 76.8. That is indeed the smallest. Okay, so now that I found the value which minimizes my distance, let me go back to my question and see what they want. And it says, at what time were the two trains closest together? Okay, so after 0.59 hours after 10 a.m., but it's always nicer to give that answer in terms of an actual time. So 0.59 times 60 minutes is 35.4. So our answer here would be at about 10:35 a.m. That's when the minimum would be. Okay. So again, quick recap here. It's all about how you set this up. Okay, and when you're drawing your picture, try to always draw it at some random time between inside your interval. So one train started from the station, whereas the other one was going towards the station. So it's starting at some point depending on the directions that you're given. Okay, that's it for this one.